I'm Sergey Sinitsa, a PhD student at Reichman University under the supervision of Dr. Ohad. I'll be presenting our paper, Deep Image Fingerprint Towards Low-Budget Static Image Detection and Model Lineage Analysis. Feel free to visit our project page for additional content. Nowadays, high-quality image generation is widely available and widely used. For instance, these two images were generated by the lead 2, and even now it's difficult for us humans to tell if these images are real or fake. Image generation has advantages, but there are also risks. For example, these two images are fake. They show infamous public figures in weird situations, and these images went viral on social media. Fake media has a deception potential. Current detection methods demand large image datasets for training and are limited to a small set of image generators. On this table, we may see results for two of those detectors. Both of them were trained on large datasets of ProGAN images. The left one can detect images generated by ProGAN only, and the right one also detects images generated by other GAN models. Yet, in both cases, they cannot detect images produced by diffusion models. So there is a lot of effort, but no robustness. We want to reduce the data budget for fake image detection. Before moving on to our method, let's discuss two concepts. First of them is CNN fingerprints. CNN models produce images with high-frequency artifacts. To reveal these artifacts, we need to extract the residual of an image. To do so, we simply take a denoiser, denoise the image, and then subtract the result from the image. We may see that the residual is basically the set of high frequencies of the image. To reveal the pattern which is hidden within the residual and basically the pattern that model produces, we need to average a number of residuals. By averaging, we reveal the clear pattern, and this pattern is referred as fingerprint because these patterns are unique per each model. Here you may see the example of this pattern for the Mini. On the left is pixel space and in the right is Fourier space. Another concept is deep image prior. Authors of this work explore the idea that CNN inductive bias contains image prior. As you may see here, they perform a simple experiment. They take the CNN model and optimize it with corrupt image. The input of this model is noise and the reference is corrupt image. After the optimization, they manage to restore this image without any additional pre-training that is required in other models. We take this idea further and we optimize various CNN architectures with a blank gray image. The first architecture is CNET. This model contains only convolutional layers and padding. Here we may see that after optimization and looking at the residual, this model produces boundary artifacts that are a result of padding. UpNet is a model that is built from one-by-one convolutions and deconvolutional layers. Here you may see a different artifact, which is upsampling artifact. Finally, UNet model generates mix of these two types of artifacts, and the UNet model is basically used in modern image generators. In our method, first we extract the image residual with DN-CNN denoiser. This denoiser is trained prior to our optimization process and is not updated during the training. Now I will guide you to one of the forward pass iterations. So first thing we do is generate the fingerprint from the noise with our new model. Then we take an image, extract its residual, and calculate correlation value. Because we are working in contrastive setting, we need additional value. So let's look how it progresses. Then we calculate the distance between two of these values. Lastly, our loss function is aimed to minimize this distance for images that came from the same source and maximize it for images that came from different sources. Next, after the training is done, we build a population reference. So basically we take the train set, real and fake images, calculate the correlation with our extracted fingerprint, and calculate the mean per each population. Then we produce the fingerprint again one last time, and at this point we do not need the model anymore. Then for each test image, we take the image, calculate the correlation as before, and check the distance between mean of these populations. In this case, value will be close to the mean of real images. If we take the fake image, we'll see that the correlation value will be close to the mean of fake images. Next, we test our method on text-to-image models. As you may see here, it dominates all other non-pre-trained models, and especially it performs much better than simple average of residuals. When we're comparing our method to pre-trained state-of-the-art models, you may see that it performs the same, or in some cases even better. Same picture is for images generated by GAN models. As you may see, our method is in par with pre-trained state-of-the-art methods. Recall that fingerprints are unique per model. At this point, we want to check the behavior of fingerprint during the training of image generator. To do so, we simply train two pro-GAN models on cat images. Here is an example of the progression. As you may see, after epoch 40, the image quality is basically high, so we consider this model converged. And if we are attempting to perform cross-detection between model checkpoints, namely we want to extract the fingerprint of some checkpoint and with this fingerprint detect images generated by other checkpoints, we may see that for each separate pro-GAN model, after epoch 40, the relation is symmetric and accuracy is generally high. So we conclude here that fingerprint not changing after the convergence of the model. Following this logic, we want to test the behavior of fine-tuned models. To do so, we take a set of stable diffusion fine-tuned models and we analyze their fingerprint via cross detections as before. From here, you may see that the relation stays. In addition, other detection methods, do not reveal this useful information. Finally, we are going back to our dataset of text-to-image models, and we want to try to detect images from one model by using the fingerprint of the other. As you may see here on this chart, the relation between Midjourney and Stable Diffusion 1 is similar to the relation between the model and its fine-tuned versions. So from here on, we conclude that Midjourney was in fact a fine-tuned version of Stable Diffusion. This is all for our study, and you are welcome, of course, to check out our paper and our project page for additional information and additional content, including datasets. Thank you.